Lenses and how they work. A lens is essentially a transparent material, it's usually glass or plastic, used to bend, refract, focus light. Lenses generally are not very useful unless they are thin. Thick lenses don't work real well. I mean, they can work, but they have some problems. We'll talk about that later. They function very similar to how mirrors worked, except they bend or refract light instead of reflecting light. Like mirrors, there's two types of lenses. There's converging lenses. They bring light together, like in this left example, this left picture, to a focal point. Or they're diverging lenses. Sometimes the diverging lenses are called negative lenses. The converging lenses are called positive lenses. But the diverging lenses disperse or spread the light apart. Now, lenses, when you're looking at these from the side view, converging lenses are always thicker in the middle. I'll show you another example on the next slide here. For glasses, because obviously lenses are corrective devices that we use for people to improve their eyesight, the more popular type of lenses, believe it or not, that people wear are the diverging lenses. They correct nearsightedness. Most people who wear glasses are nearsighted. Okay, so these are most people who wear glasses or even contact lenses. I'll explain that more fully in a second. But obviously there's a good practical purpose for lenses. They help us see better if we have difficulty focusing normally. Let's go to the next slide here. So in general, once again, side view of these lenses, and there's fancy names we can use and it really won't matter, but converging lenses are these three here, and there's other slight versions of this as well. They're thicker in the middle. They cause light to converge. They all work the same way. What you're going to find when we do problems, it actually really doesn't matter how you draw them. In fact, it's almost simpler just to draw all lenses as a vertical line and just know that there's converging versus diverging. I'll show you that in the examples. These three here on the right are all diverging. They're thinner in the middle. People who wear glasses, generally it's this third kind, this diverging meniscus type of glasses that you have as your lenses in your glasses, and contact lenses, believe it or not, are shaped like that. What happens with contact lenses, however, so that they stay on your eye, and I'll use blue here to show you this, what they do is they shave this little piece off right here that I'm shading it in blue. This is the side view, obviously. This piece is shaved off so that the lenses stay on your eyes. If you wear contact lenses, they have to be thin in the middle, though, to help you correct nearsightedness. The people who are nearsighted have trouble seeing far. These types of lenses help them see far, focus that light so they can see things that are far away. The equations and terms for lenses are the same as they are for mirrors. With one major exception that will become clear with the diagrams, but it does get a little confusing. I'll write it down right now. The image location, Q, is positive on the non-object side of the lens. This is opposite of what it is for mirrors. For mirrors, the image is positive distance if it's in front or by the object. I'll go through that with the examples here in a few minutes. Just to recap the equations, though, I have these on the other page. Lens power is 1 over the focal length, 1 over f. So the units are meters, inverse meters, meters to the negative 1. But we call that a diopter. That's called a diopter. We cannot use f equals 1/2 r because lenses have two sides that have two different curvatures. There's a fancy equation that we could use. It's called the lens maker's equation. So we're not going to get into that. But for lenses, do not use f equals 1/2 r. Use that only for mirrors. That's one other difference between lenses and mirrors. You cannot use that equation. But use the same magnification equation. It's negative little q over little p. That's one version of magnification. Or capital Q over capital P, the actual height of the object in the image. And the main lens equation, lens mirror equation, is 1 over little f, or 1 over focal length, equals 1 over lowercase p plus 1 over q, the object and image locations or distances from the lens. Same equation. It will look like we're doing the same kind of problems. Similar with the ray tracing, you have the same three rules. So the rules are essentially the same as they are for mirrors, except for the rays of light travel through the mirror, they refract or through the lens. They refract as they go through the lens instead of reflecting off the surface of the mirror. So the first rule is the same. And a ray of light parallel to the principal axis. Now, in real life lenses, it bends twice. What I normally show is a single bend in the middle of the lens, even though that's fallacious. The ray they're showing you here, it's a double bend. It bends when it goes in and it comes out. But we're not going to get that particular. It doesn't really matter that much. But when the light goes through, it bends through the focal point. All right. The other thing about lenses is they actually have two focal points. They are bidirectional, essentially. If you shine light from the right towards the left, there's another focal point that's the same as the focal point labeled here. I'll go over here on the left. Sometimes they call this F prime with a little mark above it like that. It's equal distance on either side. And by the way, when you do any measuring with lenses, you're measuring from the dead center on the principal axis right here, the spot in the center of this lens. In fact, a lot of time when we draw lenses, when I draw them, keep it as simple as possible. You can draw a lens as a vertical line. You don't have to. This really, is a good diagram because it shows you the actual thickness of the lens, but the thickness of the lens doesn't matter. In fact, the thinner the lens, the better, because it works better the thinner it is in general. Okay, rule number 2 actually is down here as the third diagram. I'm going to switch this to 2. The middle one I'm going to switch to number 3 to keep it consistent with what I did with mirrors. All right, once again, when you actually form images, there are millions and billions of rays of light that go through our lens. I'm showing you the 3 basic ones that help us the most in locating pictorially how a lens and how it's formed and where it's formed. So rule number 2 is the opposite of rule number 1, but what you'll notice here is this ray of light is going through the focal point on the left side and bending parallel. Once again, I'm showing one bend even though there's 2 bends. The net result is the ray that goes through the lens bends parallel to the principal axis. The light transmits through the lens. And rule number 3, which is my middle diagram here, is like rule number 3 for mirrors. In mirrors, the ray of light goes through the center of curvature of the mirror, hits the mirror, bounces straight back onto itself. This is similar. There's a ray of light that's going to be aimed towards the dead center of the lens. That ray of light goes straight through, doesn't bend. Now in real life it bends a little bit, but it's so negligible it doesn't really matter. When there's a thicker lens, it becomes more significant, but with thin lenses it's not significant. The ray of light goes through basically undeviated, unbent for all practical purposes. The final little thing they have at the bottom here from this online picture is they're putting all 3 of these together and adding their own notations. But it's those 3 basic rays that we want to draw when we do problem solving and ray tracing to locate images. Here are the 3 rules with diverging lenses. Once again, diverging lenses are thinner in the middle. Rule number 1, here's the focal point on the left. It's a virtual focal point on the left. There'll be an equidistant focal point on the right-hand side here. If I extend the principal axis, there's another focal point over here. I'm going to call it F prime. That's equidistant on the right-hand side and on the left-hand side. Basically, all lenses have 2 focal points. They can work both ways and have an equidistant focal point on either side. But in this first step, number 1, ray number 1, diagram number 1, technique number 1, a ray of light goes through the lens, it bends twice. Net result is it bends such that it diverges from the principal axis, but the backward projection here, you can see the dashed line, is lined up with the focal point, the virtual focal point of this lens. That's rule number 1. Rule number 2, actually this is rule number 3 right here. All right, rule number 2, let me do that with a blue ray on this first diagram. Rule number 2 goes like this. It's the opposite of rule number 1. Now watch carefully. If I have a ray of light starting from the top of this object, this flower, it's actually aimed toward this F prime over here, this secondary focal point. That's the same distance on the right-hand side of the lens as it is on the left-hand side of the lens. But that ray of light does not go through this lens straight. It goes through it, it bends twice, but the net result is it bends such that when it comes through the lens, it's parallel to the principal axis. All right? That's ray number 2, which is the opposite of ray number 1. You don't have to draw that one. When you do these problems for homework, you only need to draw 2 of these 3. And number 3 is always the easiest one to draw, the one that goes through the lens undeviated, because it really looks the same for all types of lenses. It's a ray of light that goes through the lens and it doesn't bend the center of the lens. So that's the easiest one always to draw. Sometimes I start with that one because you can almost never get that one wrong. It's the other 2 that people tend to get wrong because you got to watch out for which focal point the ray of light lines up with. So those are the 3 principal rays that we will use to locate images. And this third diagram they have here at the bottom shows you how they actually then get the image, and I'll give you another example in a minute. But if you want to look at this a little bit more deeply, here is your image right here, this little flower. These lenses always make things smaller. They're actually demagnifiers. And if you actually have these kinds of glasses, you can take them off your head right now and kind of put them by a piece of paper, and you can see how they make everything look smaller if you take them off your face and put them near and try to magnify things. The other lenses, the converging lenses, can act as magnifiers. I'll show you that. But these always are demagnifiers. They shrink things. The thing you actually see through them will look smaller than it actually is. When they're up close to your face and on your nose, you really don't notice this because they're so close to your face. But if you pull them off your face, you'll see that they make things small. So putting everything together in the kind of problems that you'll have for homework to locate images with ray diagrams and calculations. Same 3 things we're looking for to describe our images. Are they real or virtual? Where are they located? And what's the magnification? This particular diagram is actually mislabeled. I pulled it offline. This is not a mirror. This is a converging lens, so I'm going to scratch this off. It's not the anatomy of a convex mirror. All right, let me just scratch the whole thing off here. It's a converging lens with focal length of 20 and object location of 40 centimeters. So the vertical axis is what really is important here. That's where the center of the lens will be. But what you'll notice here, and this is the way I like to do the problems, you have F, F, and 2F. 2F is sort of analogous to the center of curvature of a mirror. But I like to do this with all converging lenses. You have your F on either side of the lens, and you have your 2F on either side, which is twice as far from the center of the lens as F is. That makes sense? So for example here, the focal length of this lens is 20 centimeters on either side of the lens, and the object is located at 40 centimeters. I will draw let's use the candle idea once again, not a T-Rex. So here's a candle with a flame. Looks not a very bright flame, but okay, it gives off light in all different directions. But I don't care about all the millions of different directions I can go. Step number 1 is to draw a ray of light that goes parallel to the principal axis. Once again, I know it bends twice, but for simplified purposes, you hit that vertical axis there, or at least I do, and it bends through F. If you have a straight edge right now, it probably will work better. I didn't do too bad freehand. So there's ray number 1. All right, ray number 2 is a ray that will go from our object through F, hits the mirror, goes through, or hits the lens, goes through, bends twice, but net result is it comes out parallel. It's the opposite of number 1. All right, number 3 now is optional because I've already located where my flame image is. The image of my candle is going to be where those 2 rays already intersect, so that's where the flame is, the fire. And the candle I can see is going to be upside down here, kind of like with my converging mirror, the first example. But I'm going to do ray number 3. Ray number 3 is a ray of light that goes through the center of the lens, doesn't bend, and I'm almost cheating a little bit, but I'm doing it freehand, so give me some slack here. That's ray number 3, a ray of light that goes through the lens that doesn't bend at all, essentially. All 3 of those, mine came out perfect. Like I say, I'm cheating a little bit. They all came out in exactly one spot. That's where the image of the flame of the candle is. The candle will actually be now upside down, located on close to 2F here. All right, so that black dot I'm drawing is actually the flame of the candle. That's my image. All right, if I do the calculations here, and once again, I could draw a lot more rays. There's millions of other rays of light. I wouldn't do this on a homework. Once again, on the homework, I would just draw 2 of these 3. But just to show you, Now I can draw any kind of random ray of light. So there's a random ray of light from the flame. It's going to map onto that same spot. Here's another one that goes just randomly. It's going to map onto that spot. And if I do the same thing from any other part of the candle, like the middle part of the candle, if I put a spot right here and just repeated the whole process, that red spot there from the middle of the candle, if I drew all these rays of light that's reflected off that, it's not actually giving off light. It would have to be illuminated with, well, the flame, the light from the flame or from some other outside source. That red dot from the middle of the candle would map onto the red dot on the image, which is in the middle of the image, and so on and so forth. Millions of rays of light actually form the image, but 2 or 3 from a problem-solving standpoint will locate the image. Now let's do it by calculation. Once again, basically the same equation we use for mirrors will come into play here. 1 over little f equals 1 over p plus 1 over q. You can do this even if you didn't do the diagram. F here is given as 20, 1 over 20 equals 1 over 40. These are all in centimeters, make sure they're all in the same units, plus 1 over q. If you do the math here, q comes out to be positive 40 centimeters. This is enough to really describe almost all the things we need to know about our image. Part A, okay, is it real or virtual? Well, from the diagram we can see it's real. It's flipped. It's formed by actual rays of light coming together. But if you didn't have the diagram, since 40 is positive, just like for mirrors, that means it's a real image. If the 40 was negative, and once again, real images appear on the right-hand side of lenses. They appear on the left-hand side of mirrors. So with lenses, this is the one difference. The real territory, quote-unquote, is to the right of the lens. So Q is positive to the right of the lens. It's the one thing that's different from lenses than mirrors. Part B, well, the location is 40 centimeters. That's what Q is. We just have that circle up above there. And part C, what's the magnification here? Well, magnification, to compute that, is negative Q over P. So it's negative 40 over 40. So M is negative 1. The negative means it's flipped, and the 1 means it's the same size as the object. Turns out that if you have an object on twice the focal length, the image always comes out as real, and on the twice the focal length on the other side with a magnification of 1. So that's one example of how lenses form images by bending light.